Here I give you a simple example of a single loop circuit. Let's say we have a circuit with a EMF device and a resistance R. As you know, the current must be out from the positive side. We get the current out, up. The current will pass in the circuit. Here I want to calculate the value of the current. You know the loop rule, summation of delta V equals to 0. Here we have to put you have to label each node or each point between the device here and the resistance. We can say, we can label B. Here we have C, here we have D, and here we have A. First of all, I want to start from the device. You know, we can say AB, delta V AB plus BC plus CD plus DA. Okay, between B and C we have nothing, so we don't have delta V between them. Between D and A we have nothing, so we don't have a difference of potential. Delta VAB, you know, B is at the positive side. As you see here, we are going from, we pass from A to B, B to C, C to D, D to A, and this with a loop like this, okay? From B, C, D, A, B. Okay, and this example, I will pass from B, A, D, C, B, okay, anti-clockwise. Now I am going with a clockwise direction. From clockwise, I mean from A to B to C to D to A, okay? So as I said, B is at the positive side, so VB is greater than VA because A is at the negative side. So delta V AB, which is equal to VB minus VA. VA is higher than VB, VB is higher than VA, so this value must be positive, which is equal to plus the voltage E. Okay, so VB minus VA equal plus E. What about the resistance? As you see, this is the direction of the current. The current comes from the positive side to the negative side. C is at the positive side, so VC is higher than VD. D is at the negative side. So delta VCD, which is equal to VD minus VC, VD is less than VC. So this value must be negative. You know, the voltage at the resistance equals to R times I. Must be negative, so we have to put minus. So equals to minus Ri. The summation of voltage equals to E minus IR equals to 0. So I equals to E divided by R. This is the value of the current in the loop. Now let's take the counterclockwise from A. We can say A to D to C to B to A. Okay, counterclockwise direction. Let's start from A to D. You know, summation of delta V equals to, we start AD, delta V AD plus delta V DC plus delta V CB plus delta V BA. We have to start from A to A, okay? We start by A, we have to arrive to A. Okay, between A and D, we have nothing, so delta VAD equals to 0. Between C and B, we have nothing, so delta VCB equals to 0. We have to calculate delta V DC and delta V BA. Delta V DC equals to V final minus V initial. You come here, look well. The current must be from the positive charge to the negative side, positive side to the negative side. So the voltage of C is higher than the voltage of D. VC is higher than VD. So this quantity must be positive. You know, the voltage at the resistance equals to I times R, must be positive. I times R. What about the voltage at the EMF? Here we have delta V. We have delta V AD DC CB BA, BA, which is equal to V final minus V initial, final initial. B is at the positive side, so VB is greater than VA. VA minus VB must be negative because VB has a higher value than VA. Negative, I mean minus E, minus E. Finally, the summation of delta V equals to IR minus E equals to 0. So I equals to FE divided by R. So we get the same result as the clockwise calculation. So in this case, you can do the clockwise trajectory, or you can take the anti-clockwise, you get the same. An example of multi-loop circuits. Here we have a circuit with two loops, 1 and 2. We have two batteries, E1 and E2. As you see, I have no idea about the current at R1, R2, and R3. I don't know if I1 is down or up, okay? Because we have two battery. And I don't know if I2 will be down or up. Also, I don't know if I3 will be down or up. In this case, what we have to do? We have to use, we have to draw an arbitrary direction of current at R1, R2, and R3. Okay, for example, I take I1 down, I take I2 up, and I take I3 down. But be careful. If you take any junction, we must have I in and I out. You cannot take all the current out or all the current in. For example, here I took I1 out, and here we have I3 out and I2 in. Okay, for example, we must have I in and also I out. Here in this case, we have I in equals to I2, and we have I out I1 plus I3. We can take another configuration. You can take, for example, I2 plus I1 in, and you can take I3 out. You can change as you like, but you must have I in and I out, and you do the equality to get the first relation between the current. Okay, so at this node, we can apply Kirchhoff's rule. Here we have I1 out plus I3 equals to I2. So I1 plus I3 plus I2 equals to 0. This is the first equation. The second one, as you see, we have to choose or to apply loop rule. You can take this loop, for example, A, B, D, A, A, B, D, A. By using this loop A, B, D, A, we get a relation between I1 and I3. You can take another loop. For example, we can take this loop B, C, D, B. B, C, D, B. By using this loop, we get a relation between I3 and I2. Also, you can take another loop, for example, this one. A, C, D, A. A, C, no, we have to take, look here. We have to take A, B, C, D, A. Because here between A and C, we have two battery. So we can choose A, B, C, D, A. By using this loop, we get a relation between this one, I1 and I2. So we have I1 and I2. Anyway, we have one equation, 2, 3, and 4. I need only 3 equations to find the value of the current because we have 3 unknowns. In this case, we need only 3 equations to find the values of this current. I will choose this one, and this one. Okay? So let me start with the first loop. A, B, D, A. Here in this loop, this one, we take clockwise loop. You know, delta V, the summation of delta V must be equal to O, equals to delta V AB, delta V AB at the battery E1 plus delta V BD, BD at the resistance R3 plus delta V DA. We have to start by A and we finish by the same letter A, equals to V final minus V initial plus V final minus V initial plus V final minus V initial. Here, the most important is the sign of the first V, this one, and this one. Look, here I choose the current down, so we put here plus and here minus. Here we choose the current down, so we put here plus and minus. The current must be started by positive and to the negative. Okay, VB, VAB. Okay, you know, we start with B. B is at the negative sign, so we put minus E1. VDB, DB. D is at the negative sign, so we put minus. The voltage at the resistance equals to I3 R3. AD here. A is at the positive sign, so we have plus. The voltage at this resistance equals to I1 times R1 equals to 0. This is the second equation. Okay? Now I take the second loop. The second loop, this one, clockwise trajectory. I take the loop B, C, D, B. Summation of delta V equals to O, equals to delta V BC plus delta V CD plus delta V DB. Okay, equals to V final minus V initial plus V final minus V initial plus V final minus V initial. As I said before, we look to the first one, the sign of this voltage. We come here, we look to the direction of the current. This one will start from by plus to minus, and this one from plus to minus. Here VCB, okay, delta V BC, I mean here. VCD C is at the positive sign, so we have plus E2. VCD, CD is here. VD is at the positive side, because here we have D and here we have D. D is at the positive side, we have plus. The voltage of the resistance here equals to I2 R2. Delta V dB. dB is at the resistance R3. VB is at the positive side, so we have plus times the voltage equals to 0. This is the third equation. Here we have 1, 2, and 3. Okay, I will write this relation as you see here. Equation 1, 2, and 3. You can solve them by using the calculator to get the value of I1, I2, and I3. As I said before, if I1, for example, equals to 5 ampere, in this case, we choose the right direction of I1. If I1 equals to minus 5 ampere, in this case, we have to change the direction of I1 and we keep the magnitude equals to 5 ampere. Okay? And the same for I2 and I3. We can apply the same thing. If I is positive, you keep the same direction and magnitude. If I is negative, you have to change the direction by keeping the same value of magnitude and unit.